Welcome back, everybody. Today we're going to keep plugging away and playing around with our bag of integrals here from our 7.5 worksheet. Last time we talked through the first few of the integrals up top here. Today we'll talk through 4, 5, and 6. Let me mention, though, that while we won't make video solutions for the challenge integrals down here, I definitely encourage you to spend some time with these and work on them. They're great problems that combine different techniques a lot of times, and so they are really nice integrals for getting a more flexible feel and comfort using our different integration techniques. Okay? So those are valuable problems. I encourage you to play around with those. All right, well, let's start in and look at our integral number 4. And so here, looking at this, what catches my eye right off the bat is the square root and the fact that inside of it we have two terms, right? One of them are kind of looks like something squared, and so right away this is calling out to me to do trig sub. And so in order to start trig sub, I'll just bring down a ways. Right, we want to get it into one of our nice forms, and here this isn't quite there yet, right? Because of the 4, this is actually, some number times x squared minus some number. We want to get it just into like our variable squared minus a number. And so let's go ahead and start things off with a u sub to try and collect this 4x squared as something squared, right? And in order to do that, what that something's going to have to be is 2x, right? And so right there, that 2x, that's what we want to call u, so that when we sub, we get u squared, right? Just our variable squared. And so here we work through that. There's u du. Divide the 2 over to solve for our dx, and at this point we can sub these in, right? Our dx up top, that becomes the 1/2 du, and here I've taken that 1/2 and just pulled it out front. Inside the square root, right, the 2x is going to become u, and we'll get u squared minus 1. And we just have to be a little bit careful doing the sub for the x here, right? Our x, we actually have to solve for using our substitution, right? So here we'd have u over 2 is x. And so that's what we'd have to plug in here. You could have also plugged in perhaps u over 2 for this x, and then the 2's will cancel, and you'll be left with the same thing over here, u squared. But anyways, outside the square root, the x squared becomes u over 2 squared. And before going on, let's maybe just deal with this because we have a fraction in the denominator. So if we take that squared and distribute it to the numerator and denominator, get u squared over 2 squared. And since this 4 is here is in the bottom of this fraction in the denominator, we actually, if we kind of, if we want to rewrite this, this 4 is going to flip up to the numerator. Let's see if I can convince us of that. Essentially, right here, forgetting about the square root bit, we essentially have 1 over u squared over 4. And so we have a fraction in the denominator. If we flip and multiply, that will give us 4 over the u squared. And that 4 we can then pull out, and that'll land up here where the 1 was over the 2. And so our constant multiple out front will simplify down to just a factor of 2. And we're left with just u squared there outside the square root in the denominator. At that point, things are looking good. All right, inside our square root, we have our variable squared minus some number, and so we can go ahead and do our trig sub substitution. Right, and looking at the form here, this is going to match our Pythagorean theorem identity for our secant substitution. Right, and here our number here is just 1, and so our scaling is just going to be root 1 or 1. So our sub is a nice clean u equals secant theta, and here's our differential, and we can sub that in. All right, so the du gets replaced with what it equals, and wherever we see a u, we plop the secant, and so we get left with this here after we substitute. And now, right, the whole point of this trig substitution is now underneath this square root, we have 1/2 of our Pythagorean theorem identity for secant and tangent, and we can swap this out with tangent squared. And because of our technical assumptions we're not worrying about, this just cleanly simplifies down to tangent right there. No more square roots or anything. Life is good. And now we can go ahead and just look to simplify, right? Everything's multiplied and divided. All right, so these tangents will cancel. The secant up here will cancel off with one of the secants down below. And we're left with 1 over secant as the function that we are trying to integrate. And at this point, things might feel a little bit goofy, right? We know how to integrate secant. We have that formula. It's not so pretty, but it's there. What about 1 over secant? How could we integrate that? Well, here, this is one of those times when, if we're dealing with secants and tangents, it can be really useful to write things in terms of cosines and sines. So write in terms of cosines and sines, and in particular, right, the identity here is that secant theta is 1 over cosine theta, and so since that secant is in the denominator, when we replace that with 1 over cosine, the cosine is actually going to flip all the way up to the top, and we're left with integrating the nice clean cosine. And that is an antiderivative that we know. It's just going to be sine, and so we just remember that constant multiple outside there. And so here at this point, we have integrated, and now we just need to go through, do the work of rewriting what we have back in terms of our original variable. And the way we do that is using our trig substitution. And when we did that, our sub was, we called u secant theta. And this is what we can use to get our picture of the triangle. All right, secant theta is 1 over cosine. And cosine, little thought bubble, cosine of theta is the adjacent over hypotenuse. And so since secant is 1 over that, it's going to flip them. Secant is hypotenuse over adjacent, and here we can think of this u as a u over 1. And so now filling in our right triangle here, right here is our angle theta, and so our adjacent we can call 1, our hypotenuse u, and then we just need to figure out this opposite side over here, since sine of theta needs that information. All right, so here's using Pythagorean theorem, solving for our question mark. We can find that. And so then sine of theta, right, which is opposite over hypotenuse, is going to be this square root divided by u. And so we're almost back home, right? If we remember the kind of timeline of our substitutions, we started off in terms of x, then we did a u sub, got things in terms of u, and then with our kind of trig substitution, got things in terms of theta. Here we're back in terms now of u. We need to go one step further, get things back in terms of x, and we just need to remember our substitution we did to get into u. That was letting u equal 2x, right? And so right down here, wherever we see a u, and up here. Swap those out with 2x, and so down below the 2's will cancel out. Just get left with x in the denominator, and the 2x squared will become 4 times x squared. And right there, there's a nice clean form to leave our antiderivatives. All right, well, let's move on to integral number 2. I guess it's number 5 on the worksheet. And so this one, right away, the trig is staring right at us. And so this is one of our trig integrals. And here, since we have tangents and sine floating around, let's try and get things kind of consistent. And specifically, let's go ahead and once again use this technique of trying to write everything in terms of sines and cosines. All right, and so here, what we'll be using is the fact that tangent is sine over cosine. And so if we make that switch, then we'll have sine over cosine, so we'll actually have 3 sines up on the kind of ground floor, and cosine in the basement. And at this point, it might not be super obvious what to do, and that's okay. But we do have sines and cosines going on, and we do have our strategies. And our strategies literally deal with products of sines and cosines, but we can always give it a shot. We can, up here, up top in the numerator, we have an odd pile of sines. Well, there's nothing stopping us from trying out our strategy. Let's try out our odd power strategy, and recall this says to pull off one of these factors of the odd pile, use Pythagorean theorem identity on what's left, and then do a u sub, all with the purpose in mind of getting our integral into the form of something involving a trig function with that trig function's derivative floating around, so that a u sub with u equal to that trig function will collect things nicely. And so let's play that out and see how that goes here. And so if we pull off one of these 3 sines, we get 2 left, and sine squared, we can just right away literally use the Pythagorean theorem identity. I don't need to do any more adjustments. Sine squared equals 1 minus cosine squared. And at this point, notice we are exactly in the form that we want now. And so we are happy about that, right? We have all this stuff in terms of cosine on the left, even though it looks ugly. It's all in terms of cosine. And then over here on the right, we have more or less the derivative of cosine. So let's go ahead and do a u sub. U equals cosine. Here's our du. And let's bring that negative over. And then so here we go in our substitution, the sine of x dx becomes the negative du. And I'll just take that negative and slide it all the way out front. And wherever we see a cosine, it gets replaced with u. So 1 minus cosine squared becomes 1 minus u squared, and u in the denominator. And so now with this substitution, things are looking a little bit better, and we just have to figure out how to integrate this thing. And at this point, we can kind of run back through our integration techniques. And what stands out to me actually is, here we have a fraction, just a single thing in the denominator. I think this is a good candidate for algebraically messing with this function, just breaking this up as two fractions and letting things simplify. So if we work through that, things actually go pretty well. 1 over u on the left and u squared over u. So u on the right. And both of these we are able to integrate. 1 over u becomes natural log of absolute value of u, and u through the power rule, it's u squared over 2. Right, and here I've taken this negative and I've just distributed it to both of these terms here. So on the right we get 2 negatives making it positive. And then just to finish up, we need to just get what's in terms of u back in terms of x, and so we'll swap that out using our substitution with u equals cosine. And in doing that, we get our antiderivatives all in terms of x, and this is a fine form to leave them in. All right, well, moving on to the last integral from the top group. So here, essentially we're integrating the function 1 over 1 minus x squared to the 3/2 power. And I think what maybe is natural to feel right away is a little bit of aversion to the 3/2 power. We don't normally like dealing with fractional exponents. We don't have to, but it's nothing too crazy, right? Just think about it for a second. The denominator here tells us the root that we're looking at, and so we could either see this as the square root of 1 minus x squared cubed, or we could think of it as the square root of 1 minus x squared where we cube it inside. We could think of it in either one of those two ways, or we could actually just leave it in this 3/2 exponent form. But so anyway, what catches my eye is what's going on inside. Right here we have some number minus our variable squared. And this is kind of calling out to me to do a trig sub to collect this as one term and hopefully be able to integrate. And so let's think through that. All right, so this particular form, a number minus our variable squared, this is going to match up with the sine and cosine Pythagorean theorem real nicely. And so we'll want to use our substitution with x equal the root of that number, scaling sine. And so here our number is just a nice clean 1. And so root 1 is just 1. And so our sub is just x equals sine theta. And here's our dx. And making that substitution here, our dx up top swaps out with cosine theta d theta. And down in the bottom, our x squared becomes sine squared. And here right away, we can literally use our Pythagorean theorem. It tells us that 1 minus sine squared equals cosine squared. And at this point, we have a nice kind of rule of exponents things going on, right? If we have cosine raised to a power. So let's see if we can kind of help ourselves out here. What this is literally saying is cosine of theta squared all raised to the 3/2 power. And we just have to recall here that when we take something and raise it to a power and raise that to a power, those exponents multiply. And so in this case, actually the 2's will happily cancel out, and we're just left with a nice clean power of 3. Right? In other words, cosine cubed is what we're left with in the denominator. Right, and right away we can start canceling some stuff. Cosine up top will cancel off with one of the cosines in the denominator. And we're left with integrating 1 over cosine squared. And here the question is, well, how can we do this? How can we integrate this function? Right, if it was cosine squared up top, well then we'd have a strategy for that, right? We could use our double angle formula, work through that, but in the bottom, it's not going to work so well. You know, we could try to think maybe a u sub with u being cosine of theta, since that's kind of an inside function down below. But its derivative is not really floating around, and so this doesn't look like it's going to be helpful. Well, in this case, you know, we've seen before a strategy of, you know, if we have tangents and secants, to write things in terms of sines and cosines. This one is a little bit sneaky. We actually want to go the other way. Right, 1 over cosine squared is secant squared. And I claim we know how to integrate secant squared. And if you said tangent, that is spot on. This is actually just a known formula for us, right? The derivative of tangent is secant squared, and so the antiderivatives of secant squared are tangent theta plus c. And so here, this is one that we know. Whoop. All right, and at this point, we just need to get things back in terms of x. So we use our original substitution for our trig sub here. And sine is telling us opposite over hypotenuse. And so getting a picture of our angle here, theta. Again, we can think of this x as x over 1 and label our opposite on hypotenuse. And then tangent wants the opposite over adjacent. And so we do need to figure out that adjacent side. Just using Pythagorean theorem, we can get its root 1 minus x squared. All right, so popping in the opposite x over the adjacent, our root there. We get everything back in terms of x, and this is a nice clean form to leave everything in. All right, good work today, everybody. Again, if you haven't had a chance to dig into those challenge integrals, highly encourage you to play around with those. They're great problems. If you have any questions, post those to Piazza, and I'll see you next time.